Greetings and welcome to a special lecture on the Generalized Binomial Theorem, and in this video I will also try to connect this with the souped up version of Pascal's triangle that we all know and love. Let's start with a quick recap of Pascal's triangle. For numbers on the edge of the triangle, you can just copy down the number above, so you'll just see edges which are all ones. But if there are two numbers above, so we'll add them together. So in this case, 1 plus 1 gives us 2. Now we repeat this algorithm row by row by row. Now Pascal's triangle is quite handy because it gives you the values for n choose r. And this represents the number of ways where we can choose r objects out of n objects. And the exact formula is given by n factorial over r factorial and n minus r factorial. We can also cancel n minus r factorial from n factorial to simplify this to be a falling factorial in the numerator, where we'll just take n times n minus 1 times so on and so forth for r terms in the numerator divided by r factorial. Now how can we connect this with the Pascal's triangle that we just generated? So first we need to label each row. So the first row will be n equals to 0, second row will be n equals to 1, and so on. For the diagonals, we are going to label them as r equals to 0, r equals to 1, r equals to 2, and so on and so forth. Now, if I wanted to calculate something like 4 choose 2, that would be at the n equals to 4 row and the r equals to 2 diagonal. And that will give me the result of 4 choose 2, which is 4 times 3 over 2 factorial, which is 6, which is what we wrote in that hexagon. And this allows us to transform the entirety of Pascal's triangle into this triangle where it represents the results for all the n choose r. And another useful result of Pascal's triangle is that this also gives us the coefficients to the binomial expansion of 1 plus x to the power of n. So for example, 1 plus x squared will give us 1 plus 2x plus 1x squared. And these coefficients 1 to 1 represents the entries in the Pascal's triangle for the n equals to 2 row. But must Pascal's triangle be a triangle? So quite trivially, I can add some zeros. So in this case, look, 1 plus 0 gives us 1. So the 0 belongs there. And I can add even more trivial zeros. And this is in the spirit of my obsessive compulsive disorder. I've extended the triangle into a rhombus. But can we do more? Let's go upwards to the n minus 1 row. So moving upwards along the diagonal, you can see that all the things in the light blue diagonals are 1s. So let's just add another 1. And 1 plus what gives us 0? Well, it has to be negative 1. So if I continue this pattern, I'm going to get this pattern of 1s and negative 1s. So not what we quite expect, but this allows us to extend Pascal's triangle even more into the negative territory. And we can use this process to further extend Pascal's triangle upwards. You'll see this will give us a n equals to negative 2 and n equals to negative 3 row, and this will go on forever. But the bizarre result here is that by extending Pascal's triangle, the new numbers that we get actually corresponds to the polynomial expansion for the binomial expansion where n are negative numbers. The key difference comparing this to the typical binomial expansion that we know is that these are infinite polynomials, because the binomial expansion doesn't really end. So for example, for 1 plus x to the power of negative 1, it's going to give us 1 minus x plus x squared minus x cubed plus x to the power of 4, and this goes on forever. Compared to this, the typical binomial expansion are finite polynomials. And so the natural question here is, if we extended Pascal's triangle, are the new entries, do they still correspond to n choose r? So let's look at this Pascal's triangle. So what I've done is I've labeled the diagonals again to be r equals to 0 to r equals to 5. And let's look at our definition of n choose r. We're going to use the definition that it's going to be the falling factorial. So n times n minus 1 times so on for r terms in the numerator divided by r factorial. And let's pick one of the entries, -2 choose 3, which seems like quite a weird thing. How can I choose 3 objects out of -2 objects? But this is just for calculation purposes, and we're going to see whether this does give us the coefficient for the 1 plus x to the power of -2 expansion. So our prediction is that it's going to give us -4. So let's check the calculation. So for falling factorial, my numerator is going to be -2 times -3 times -4, so 3 terms multiplied together, divided by r factorial, which is 3 factorial. So you're going to see that I do get -4. So this extended Pascal's triangle does give me the result to n choose r for negative values of n. What is going to be even weirder is, what if I want non-integer values? So let's shift Pascal's triangle. Could I work out what is the row for n equals to 0.5? So it does work, and it does correspond to the binomial expansion for 1 plus x to the power of -0.5. And let's just take one of the entries to verify. So let's look at 0.5 choose 3. So again, in my numerator, I take the falling factorial of 0.5 times -0.5 times -1.5 divided by my r factorial, which is 3 factorial. I do get 1 over 16. And this is going to correspond to my coefficient of x cubed in the expansion of 1 plus x to the power of -0.5. So some patterns you would observe is that n choose 0 will always be 1, no matter what n is, whether it is a positive integer, a negative integer, or even a decimal. N choose 1 will always be n, and n choose 2 will be the n times n minus 1 over 2. N choose 3 will be n times n minus 1 times n minus 2 over 6. So these are some patterns that we can observe. Now let's compare the generalized binomial theorem with the standard form that we know. In the generalized form, instead of summing from 0 to n, we're now summing from 0 to infinity. The second key difference is that instead of n choose r being n factorial over r factorial and n minus r factorial, now we will use the falling factorial definition in the numerator. There will be a third key difference that I'll highlight after the worked example. Let's go through a worked example. Find the first 4 terms in the expansion of the cube root of 1 plus x in ascending powers of x. So let's write down the generalized binomial theorem. We can express the cube root as power 1/3. So this is going to give the infinite sum from r equals to 0 to infinity of 1/3 choose r times x to the power of r. So we can list out the first 4 terms. Now we need to simplify 1/3 choose 1, which is going to be 1/3. 1/3 choose 2 is going to give us a falling factorial in the numerator. So it's 1/3 times 1/3 minus 1. So it's 1/3 times -2/3 divided by 2 factorial, and that gives us -1 over 9. And lastly, 1/3 choose 3 will give us 5 over 81. So we'll use these as our coefficients, and our final answer will be 1 plus 1/3 x minus 1 over 9 x squared plus 5 over 81 x cubed. Now let's look at the graph of the cube root of 1 plus x. Here shown in green. The blue horizontal line here represents y equals to 1, and this is the binomial approximation to the green curve, but only to one term. So it's not a very good approximation at all. In fact, it is only correct at the y-intercept here. So if I increase it by one more term, notice that not only do I get the y-intercept correct, but now the gradient is correct as well. So let's see if I increase it to 3 terms, the gradient is correct, and now the concavity at the y-intercept is also correct. And as I increase the number of terms, the blue curve approximates to the green curve, but only for x values between 1 and -1. When x is more than 1 or less than -1, the blue curve diverges away from the green curve. So we say that the radius of convergence for this blue curve is between 1 and -1. Hence, from the worked example, you can see that the third key difference between the generalized and standard form of the binomial theorem is that the generalized form doesn't work as a good approximation for all values of a. It will only work when the modulus of a is less than 1, and we call this the radius of convergence. Now for some practice. Find the first 4 terms in ascending powers of x for the expansion of these two expressions. Do also state the values of x for which these expansions are convergent. Pause the video here and give these 2 questions a good try. So first we rewrite this as 1 plus 2x to the power of -1. Now we use the general term for the generalized binomial theorem. So we sum from 0 to infinity, -1 choose r, 2x to the power of r. So these are the first 4 terms. Now evaluating them, you'll get 1 minus 2x plus 4x squared minus 8x cubed. Now don't forget to put a plus ... since they are not equivalent. And for our radius of convergence, x, we know that a has to be less than 1, so modulus of 2x is less than 1. That makes modulus of x less than half. So graphically, the graph of y equals to 1 over 1 plus 2x looks like this in green. So if I just use one term, it looks like this, with 2 terms, 3 terms, 4 terms, and so on. Can you see that the radius of convergence has to be between -half and half for x? So to make this in the form of 1 plus a to the power of n, we've got to take out the square root 4. So if we factor it out, we'll get square root 4 times of 1 minus x squared over 4 to the power of half. So the square root 4 is just 2. The general term is going to be half choose r minus x squared over 4 to the power of r. And this is summed from 0 to infinity. So the first 4 terms will give us this, and if we simplify it, we'll get 2 minus 1/4 x squared minus 1 over 64 x to the power 4 minus 1 over 512 x to the power 6 plus ... Now the radius of convergence here is x squared over 4, which is our a term, less than 1. So the modulus of x squared over 4 less than 1. Actually the modulus is not necessary since x squared is positive. But we'll just leave it there for now. So x squared must be less than 4. And if we simplify this, we'll get x between 2 and -2. So we can say the modulus of x is less than 2. So here is what the graph of square root of 4 minus x squared actually looks like. So if we just put one term, y equals to 2, this is what it looks like. Only gets the y-intercept correct. But if we add more terms, the approximation gets better and better. And you can see that not only is the radius of convergence between 2 and -2, there is no graph outside of 2 and -2, so all that is invalid. You can't take square root of negative numbers. So with that, we've come to the end of this lecture. So this is meant to be a bridge between the binomial theorem that you have learned in secondary school and to connect it to the A-level Maclaurin series. So I hope you enjoyed this. Thank you for your kind attention and have a great day of learning.